All right, let's learn. Okay, so watch this. Remember the last thing I taught you was about parametric equations? Oh, the notes are still there. That's good. Uh, so all we did was like remind you how they work, or maybe you're seeing them for the first time. People seem to say that they had not seen these before. So basically, all that's going on is instead of just y varying with respect to x, like instead of y just depending on x, it's both x and y that depend on a third variable t. And so if you graph, you make up some crazy equations, you can get some crazy graphs. Basically, is what's going on. Like you get that loop or you get this neat looking thing or the star here. Or if you like I said, if you just play on Desmos and you make as crazy an equation as you can with sines and cosines and tangents and whatever else, e to the whatever, put some in x and some in y, you get some cool looking graphs. But that was just like, again, that was just an intro into what even are these. Now you actually get into the calculus of them, like the derivatives, the arc lengths, and the integrals and stuff like that. So watch this. It says that if you want, basically it says that if you want the slope at any point of a crazy parametric equation, then it kind of might be what you expect, where, I mean, you guys know that slope is rise over run, as in change in y over change in x. So, as you might expect, if you get a couple of parametric equations, the slope of those parametric equations is change in y over change in x, as in dy dt over dx dt. That's how I can remember it. But another way to remember it, if you want a more formulaic way, is that if you take dy dt, but you want dx dt, then what you can do is like multiply by dt dx. Like treat them like fractions, basically, is what I'm saying. And you get dy dx, which is what you want. And multiplying by dt dx is the same thing as dividing by dx dt. Although that one seems a lot less intuitive to me because it doesn't mean much. Like conceptually, it doesn't mean much to me. But if you like the formulaic way of like treating them like fractions, then maybe that will remind you how to do it. But either way, change in y over change in x, dy dt over dx dt. And then this stuff you kind of already know, like we talked about it before, but we'll talk about it again when we get to it. But this first problem doesn't have to do with horizontal or vertical tangent lines. It just says there's a pair of parametric equations. Take the tangent line at the point where t is 2 pi over 3. Okay, so this is tangent lines, like nothing's changed about that. In fact, maybe it's good to get a little visual of what's going on. So I graphed the parametric equations. There's the x function, there's the y function. It made this ellipse. And depending on how much you remember from Friday, maybe you already would have predicted that. And then it says whenever t was 2 pi over 3, which we don't know where that is on this ellipse, get the tangent line there. So here's us doing that. First, well, okay, tangent line, no matter what the context, always looks like this. And before, we were lucky enough that we at least got one of these for free when it told us x equals 7 or whatever. But in this case, we don't even get that. So we have to get all three of these blanks ourselves. So let me just make sure you're with me. If I wanted that x coordinate, how would I? Yeah, please.
Plug it into x equals 5.
Okay, yeah, just making sure you guys are good with parametric equations. Here it tells you the x value at any point is given by 5 sine of t, so plug in t into the 5 sine. 5 times sine of 2 pi on 3, which is, here's a unit circle, 2 pi over 3 is 4 pi over 6, so 1, 2, 3, 4 right there, that point that I just made right there. So sine of 2 pi over 3, remember sine is the y value, that looks like the longer side, so that should be radical 3 over 2. So 5 times radical 3 over 2, there's my x value. In fact, before I forget, let me just plug that in right here. 5 radical 3, 2. Okay, then the y value is the same thing, but now with the y equation, so 3 times cosine of 2 pi over 3 is 3 times negative 1/2 for the same reason as before. To negative 3/2, which is going in here. So minus negative 3/2, but let me just make that a plus 3/2. Boom, and then here's the actual new part. Here's the actual calculus is when you take the slope. Remember, you got to get the derivative. So dy dx, which is what I was saying before, where you just take dy dt over dx. So here's us doing that in orange, not like orange. Let's do it in purple, no, dark blue. Again, this will give me dy dx. But dy dt is, where's the y? Here. So derivative of that would be negative 3 sine of t over dx dt is 5 cosine of t. And then evaluate that at evaluate that at 2 pi over 3, and we would get negative 3 times the sine of 2 pi. Let me just write it all out before I have to do it all in my head. Negative 3 times the sine of 2 pi over 3, I meant. Over 5 times the cosine of that. Equals what we say the sine was, radical 3 over 2? Yes. So negative 3 radical 3 over 2 over 5 times negative 1/2, so negative 5/2. Boom. There you go. There's your slope. And then that goes into the slope like slot. Yes? No, say.
For the 5 side of the cosine t, is there like the t of the side apply and then just cancel out? Or is it not? It does not work like that.
Oh, no. Oh, I see what you're saying. No, this is like sine of p and cosine of p. So no, it doesn't work that way.
Oh, like it's not a function inside.
Correct.
Oh,
Yeah, correct. This is just straight up speed and straight up speed. Like that. Okay, there you go. So you can put this in for the slope, but just to make it look nicer, this blah 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 over 2 and this blah 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 over 2, the 1/2s there can cancel. If you don't believe me, you can keep change flip, but take my word for it that will happen. Oh, and also the negative. That's actually not that bad. So final slope will be 3 radical 3 over 5. Boom, we did it. Equation of the tangent line. And if you don't believe it, let's check it. Watch this. I'll grab my key so I don't forget it. We said it was y plus 3/2. Y plus 3/2 equals 3 square root 3 5 times x minus 5. Sorry, there it is. That looks like a good tangent. Nice, y'all.
Right, thank you. That was my 3D.
All right, questions on that? Nice. Okay, next one, I think, actually, I don't remember if it's the second derivative one. Yeah. Next one asks for the second derivative, as in the second derivative of y with respect to x. So this guy right here. And I'll tell you about that in a second. But of course, for that, you're going to need to find the first derivative. So let's do that really quick. So first, let me find u by dx. Actually, first, let you find u by dx. Again, if you missed it, this is only a little bit of a problem because we get functions of t and functions of t, so you have to do the thing we did in the last problem, where you divide the y by the x. Okay, check that you got the same dy dx as me, this. And then if you wanted to, you could even simplify this a little bit. Because everything has a 2t as a factor. Which you can cancel to get this. See what I'm saying? And I'm only doing that because then it makes the second derivative easier to think. But I hope you agree with that. The only thing is that if you want to, if like your math teacher should tell you that technically this function is not the same as that function because this function that I'm well, the people in the video can't see, but this function that I'm circling right now with my mouse is undefined when t is 0, and this function that I'm circling with my mouse now is defined at t equals 0. So technically, you should say that t can't be 0 here, and now they're the same function. But that's me really being very good. Now, there's my first derivative. My second derivative, if I were to ask you without like if you didn't feel like I was trying to trick you and I asked you how do you take the second derivative of this, I think you guys would all say just take the derivative of that. But the thing is that this is a function of t, so you're kind of taking the second derivative with respect to t when you really want the second derivative with respect to x. So for similar reasons as before, in fact, maybe I'll show you, like I try to convince you in a second, but basically we'll take the derivative of this, that'll give me this. I don't even know how to write it. It'll give me something like that. Because this is the this is the derivative. Yeah, let me try to convince you later. Because I don't want to get into it, because it's actually very easy to do. So you will take the derivative of this and then divide it by the change in x again. More on that later, but let me just let's just do it and then I'll try to convince you. So the second derivative of y with respect to x would be just like you would have imagined, take the derivative of that, that's 30t squared minus 9. But then over the original dx dt. So that would be 30t squared minus 9 over, what was it? 2t. Nice, yeah, it is 2t. Over that. That's your second derivative of y with respect to x. Okay, and then now let me convince you for real, but I guess I'll do it right here on the side right here. And what I'm saying is that if you have dy dx, which is what we had before, and then you take the derivative of that with respect to t, then you don't get, again, I'm going to try to convince you with a fractions argument, that if you do this to dy dx, as in you just do it with respect to t, then what you get is this. And again, just bear with me, treat these like fractions for a second, which is not what you want. You want a second derivative of x right here. So that's why I'm saying if you divide by dx dt, or in other words, multiply by dt dx, then again, fractions argument would be like these can cancel, and now you have your two dx's, so you get that. And to me, in my brain, that's how I remember. I just have to like remind myself to divide by the extra dx dt. I don't have to think real hard about conceptually what's going on here with dividing by dx dt. But basically, it's like if you got to divide by the extra change in x if you're taking another change in y. But again, see me one-on-one, and maybe I could work out what's going on conceptually. But okay, second derivative, there it is. I've seen this on the AP test, like they ask it on a multiple choice question, and like they try to trick you about forgetting to divide by this, but don't forget to divide by that. Okay, we still have that. Okay, and then next one says find all the points where the tangent line is horizontal and where it's vertical, giving those parametric equations, which all has to do with the slope of the function. So do you guys remember how to find, like, let's just talk about horizontal tangent line. Where would that happen?
Top is 0.
Yeah, where the derivative has, like, where the slope is 0. In other words, where dy dx is 0. In other words, where the top of the fraction is 0. And then vertical tangent line, do you remember that?
Bottom is 0.
Yeah, exactly. Where the bottom of the fraction is 0, because that's where the slope would be undefined, which would mean that the x dt is 0. But let's get there. First, let me find dy dx, because I need to know about the slope if I'm going to know about the tangent line. So here's us finding dy dx. That's an x, which again is dy dt over dx dt. Okay, dy dt would be derivative of that. And dx dt would be the derivative of this. Or sorry, the other one. Okay, and then if you didn't see it before, here's what Sam was saying, is that here's the slope of my function at any point t, or at any time t. If this is going to be horizontal, then the slope needs to be 0, meaning the top has to be 0. And if it's going to be vertical, then it needs to be undefined, so therefore the bottom has to be. Okay, so here's us checking horizontal. Horizontal happens when the top of this is 0, which would mean that t is 4 if I skip all the steps. Like add 8 and divide by 2, you get t equals 4. And then vertical happens when the bottom of that is 0. Again, that gives you an undefined slope, remember, and vertical lines have undefined slope. So I skip all the steps. I have 6 and I divide by 6 and I get t equals 1. And then you guys are saying, oh, sweet, we did it. Move on to the next one. Wrong, though, because why? Yeah, good job. Yeah, good job reading it closely. Let's find all the points of horizontal and vertical tangency. So they want the x and the y coordinate, which is just one more annoying step where you take this, plug it into x and y, take this, plug it into x and y, and there you go. So let me organize this a little better. There's me doing some work to find out the t values, and then here's me finding the x and y coordinates. So that would mean x is 3 times 4 squared minus 6 times 4, which is, I don't know if I'm going to do that in my brain. I will check my key and get
44.
okay. Yeah, 24 sounds right. Yeah, okay. I thought I had done it wrong if you said 0. But yeah, I have 24, comma, and then y is, well, let me leave it like that. Y is 4 squared minus 8 times 4 plus 9 is -7 according to my notes. Therefore, the point of horizontal tangency would be 24, comma, -7. Boom. Oh shoot, this is vertical or it's horizontal, isn't it? Or is nice. What's up? Did I lose you? Okay. And then the vertical tangent line, what do we say? T equals 1. So here's us from 1, x equals 3 times 1 minus 6 times 1 is -3. And then y is uh, 2. There you go. Final answer. This. Okay. Questions so far? Okay. Then the last little bit that you have to learn is about arc lengths. Which I think not any one part of this is hard, but it is like in one section I give you 3 different formulas, which you may or may not see where these come from. So it might be hard to keep track of these, but if you do your I forgot to print your homework. Yeah, I'll print it today and give it to you tomorrow, and then you can practice it. Sorry. But I'll do it today, and then you can have some practice. And then again, I'm not gonna grade them like for a real grade. So it's just like do as many until you feel like okay, I got this, and don't feel like you got to do every single problem. But anyway, do your homework because that way you will solidify all these 3 different formulas that may not mean much to you right now. But anyway, what I was saying is that the last thing in this little section is about arc lengths, which is something that you learned before in just normal rectangular functions, but now you got it in parametric equations. But they come from the same place. In fact, do you guys remember for normal functions, for normal rectangular, what the arc length formula is? Yeah, there's the one in there. Nice. Do you remember it?
Wait, I mean, where 1 plus what? Yeah.
Square root of 1 plus dy dx. Nice, except nice, yeah. Yeah, that's it. It's 1 plus f prime squared. If you look at this should look familiar because they come from the same place. They both come from here, let me do it down here. You don't feel like you gotta write this, but just so you don't feel like this is a random formula, they both come from the distance formula, which is this, the Pythagorean theorem. And without getting into all this little tiny details of that, remember you're basically taking 2 points that are really close together. So you're taking the limit as these gets really close together. And then the way this one came about is that we divided by the independent variable x, and we got x over itself is 1, and then y's over x's, as those get really, really tiny, is the change in y or changing x. In other words, the derivative of the function squared. Y over x, change y over change in x, slope, derivative. Boom. And we do the same thing this time, but now divide by the new independent variable, not x, but t, then you get that. If you divide everything by t2 minus t1 squared, then you can see you get change in x over change in t, dx dt. Change in y over change in t, dy dt. So that's basically where that comes from. Again, that's not me getting into the details. That's me giving you the intuition. If you wanted the details, it wouldn't be that much harder, but it would be much uglier. Okay, with all that said, here's your arc length formula. If you can remember this one, then I think you can remember that one too. Like again, they come from the same place. That's how I remember them. I start with the distance formula and I'm like, okay, is it T's or X's? And then divide by the independent variable. All right. But the actual problems are pretty easy. The only times I've seen them is like find the arc length of whatever, and you just follow the formula and you're done. And like I said, most of the time these are very ugly to do by hand unless they really handpick the formula, the equations to be easily integrated. So even more so, they're pretty easy. You just set up the integral and you're done. One thing though is that I doubt he meant to put 2t cubed over 2 because those would just cancel. So I bet this was a 3 that he wanted to put down. But I don't know. But otherwise it'd be silly. So change that to a 3. And then, like I said, now I just got to do. Let me find what dx dt is. Let me find what dy dt is. And then put those into the integral, and I'm done. Does it say 0 to 2 of this squared plus this squared dt? And that, again, if you put that into your calculator, that should give you this number, 6.0109. So
It's 2t squared squared. Right?
nice. Yeah. Yeah, my bad. All right. Questions on that one? Okay. Then this last one is fun, but I don't want to do it with like 3 minutes left. So, or 8 minutes, whatever. I don't want to rush it. So let me leave that for next time, and we'll do 9.3 as well. So let me stop there. If you have questions, I'm here. Again, I'll get you your homework tomorrow for sure.